The study titled Momentum of a Divergence-Free Fluid in a Cubic Domain explores the choreography of fluid moving in a complex helical, or corkscrew, pattern. It focuses on the tension between how a fluid moves locally versus how it behaves when viewed as a whole within a specific boundary. The nature of the flow. The fluid is described as divergence-free, a technical way of saying it is incompressible. Like water or oil, it doesn't compress or expand. It simply flows. In this specific model, the fluid is doing two things at once. It is spinning like a solid cylinder while simultaneously rising steadily upward. The rigid body paradox. A central theme of the research is the distinction between different types of rotation. Local spin. In this helical model, every tiny parcel of fluid is spinning around its own center, much like a solid rod would if you twisted it. This is known as rigid body rotation. Global asymmetry. The study places an observation cube off-center from the main axis of rotation. Because the cube only captures one slice of the swirling flow, the spinning motions don't cancel each other out. This leads to a paradox, where a simple, synchronized local movement creates a complex, lopsided momentum when viewed globally. The fluid inside the box isn't just swirling, it has a collective bias or net push in a specific diagonal direction because of where the box is sitting in space. Bridging the gap with lever arms. The research uses the concept of orbital momentum to explain this bias. Because the fluid mass is a certain distance away from the central axis, that distance acts as a lever arm. As the fluid moves upward, this offset creates a distinct tilt in the total rotational energy. This bridge explains how the microscopic spin of individual fluid particles synthesizes into the macroscopic, asymmetrical movement of the entire body of fluid. Interactive learning. To make these abstract concepts tangible, the page provides comparative demos, visual tools that contrast rotational flow, where particles spin, with irrotational flow, where particles orbit but stay facing the same direction. Logical frameworks. Sequence and state diagrams that track the transition from theoretical physics to real-time visual simulations, helping researchers visualize how spatial orientation dictates the physical properties of the flow.